I believe in an introductory course in survey sampling as an undergraduate student with statistics honors or major, we get to touch upon simple random sampling with and without, stratified sampling, systematic sampling, cluster sampling, then the ratio and regression estimators, if not anything more. So, I will take the liberty of not going into the traditional sampling methods beyond the stratified sampling that I took up. Now, I will go for an entirely new world of what are known as unequal probability sampling designs. There is a vast literature on that. There are practical issues involved, compelling one to talk about unequal probability sampling, and there are estimation methods, there are sampling methods, a lot of things to learn which is not covered in undergraduate course. So, we will have a test of these things in this module and in the module that will follow. Okay. As I said, in this module we will take up unequal probability sampling. Those, I hope you realize that under with and without replacement sampling, in a way there is a feeling that all the population units are treated equally with equal importance. That is why we are talking about random sampling. Whether it is with or without, that is a matter of whether we repeat the selected item or not. But otherwise, there is no preference to one item as against the other. Looks like all the population units are regarded equally in their own right. However, there could be a problem.
Do you mean to say once the units in the finite population have been identified and labeled as 1, 2, and capital N, we treat the units with equal importance? Yes, I can see that. By the nature of sampling, be it with replacement or without replacement.
Technically, under with replacement, we note that chance of inclusion of any unit. So, the meaning of chance of inclusion of any unit means what is the chance that, for example, unit number 1 will be included in a sample drawn according to with replacement sampling. Because there is a possibility of repeat, you always go by negation. Chance of inclusion is 1 minus chance of exclusion. That exclusion means total exclusion from every sample. That is why 1 minus exclusion from every sample is n minus 1 over n whole to the power n. That means the unit is totally excluded. So, 1 minus that is the chance of inclusion in at least one place out of n trials that you are making. That is the idea of getting this result. So, chance of inclusion of any unit is 1 minus total exclusion, and similarly the chance of joint inclusion, you refer to simple computational formula for probability of two events intersection, you get to see this result 1 minus 2 times this quantity plus this quantity.
I think I can follow the computations fairly easily. By the same token, under simple random sampling without replacement, capital N, small n, we must have 1 replaced by small n over capital N, and 2 replaced by small n times small n minus 1 divided by capital N times capital N minus 1, right?
Yes, very much so. Anyway, don't you think this is too much to attach equal importance to all the population units? Who knows, in applications we have large units, small units, whatever that means. For example, if it is a household survey, there could be houses with a big house, there could be a small house only, small few members. So, why are we giving equal importance, attaching equal importance to all the population units? Maybe we should deviate from this. Simple random sampling, maybe that is not the way we should go in reality.
Sir, I can see your point. For example, when we contemplate on collecting household surveys, the household sizes are likely to be different, and so we might like to attach more importance to households of larger sizes. In a way, we should develop a framework for unequal inclusion probabilities to the extent possible.
Yeah, this is what I wanted to point out to you. This household survey, the same thing we both are talking about. Why is it that a household of size 3 and a household of size 10 should have equal importance? There is no logic in that. That is why there is a compelling need to talk about and introduce what are called unequal probability sampling schemes. Okay, so there is a very general class of schemes, maybe whether it is with or without replacement, that's a different thing, but accordingly we can call probability sampling with replacement, probability sampling without replacement, but we must attach this unequal probability qualification. We need to develop the estimation procedure, first the sampling procedure, and then the estimation procedure all over again. Let us think logically. There are capital N population units in a finite leveled population. It is believed that the units have some distinguishing features attached to them, so that we have enough reasons to go for unequal probability sampling. And the household survey is a classical example. We must understand the phrase unequal probability sampling. Do we mean at every stage of the sampling operation the units are to be treated with unequal probability, or on the whole we should refer to unequal inclusion probability, maybe also to unequal joint inclusion probability? That's a good question. Let's try to understand again. When we say sampling, so are we talking about sampling one at a time? So if my sample size is 5, I pick up one. If it is without replacement, I pick up another distinct from the first one, etc. And is it that every stage the units are to be treated with unequal probability? Is that the impression that we are trying to get when you say unequal probability sampling? Or is it that on the whole, when the sample has been selected, there is an unequal inclusion probability for everybody, also for joint inclusion probabilities, it has to be unequal for different pairs? So what kind of thing are we referring to?
Sir, is there any difference between the two terms you're using? I thought these ought to be interpreted in the same way. Maybe not. Maybe there is a difference.
Let us be critical about it. First, with replacement sampling, etc., etc., let there be chancy weights P1, P2, P capital N attached to the capital N population units to start with. So it could be that the relative size, the size of the household divided by the total size of all the households together, that serves as the weights that I am talking about. P1, P2, P capital N, they are all positive, they add up to 1. The fact that summation Pi equal to 1 suggests that Pi could be taken as the actual household size divided by sum of all the household sizes in the population. If I have advanced knowledge of all the capital N household sizes, I can think of Pi and I can use Pi as the chancy weight for selection of the ith household. That makes sense because you are giving more chance to the household having more number of households and less chance to the household having less number of households. So we can critically think about with replacement sampling, and then we can think of chancy weights P1, P2, Pn to be attached to all the capital N population units to start with. What we are exactly talking about, we know, for a given sample size under with replacement sampling, each time we select one population unit using the probability vector P equal to P1, P2, Pn. So this P1, P2, Pn, it stands as a probability vector for ensuring selection of the units according to the probabilities P1, P2, Pn in every term if we are talking about with replacement sampling. Okay? So first unit is selected using the allocation probabilities P1, P2, Pn. Then again, next unit is selected using the same allocation probabilities, etc., because we are referring to the framework of with replacement sampling. I hope this part is very clear.
Yes, sir. I can also compute directly from the definition. Inclusion probability of unit I is 1 minus pi whole raised to the power n.
That's very true, because 1 minus pi refers to exclusion probability of the unit I. And if I am referring to with replacement sampling n trials, in every trial the exclusion probability is 1 minus pi. Therefore 1 minus pi whole to the power n, that is the total exclusion probability for the unit I. And 1 minus that is the inclusion probability of the unit I. Same interpretation, that means the chance that unit number I is included in at least one of the small n trials. What is the next one?
Joint inclusion probability for units I and j is 1 minus pi raised to the power of n minus 1 minus pj raised to the power of n plus 1 minus pi minus pj raised to the power of n.
This is a simple probability problem involving inclusion and exclusion of units. Okay, this is not difficult. These are pretty obvious.
I can also see that these inclusion probabilities are entirely different from the PIs, albeit these are related, no doubt. I do think such expressions for inclusion probabilities, single or joint, are likely to be very complicated under without replacement sampling.
Yeah, so one thing is, as you rightly said, these inclusion probabilities are not quite PIs. 1 minus 1 minus pi to the power n, it is nowhere near pi, or the joint inclusion probability is nowhere near pi pj, even though they are all related. So it is good that we need to know, and also you made a very good remark that without replacement sampling, things are not going to be as easy as this, okay?
Let me try out the case of n equals 2.
You mean sample size 2, okay.
I think I can argue that the inclusion probability of unit I, pi I, is pi plus summing over all the j's unequal to I, pj pi divided by 1 minus pj, which ends up as pi 1 plus summing over j's not equal to I, pj over 1 minus pj.
You are very right. Let's try to argue out once more. Because the sample size is 2 and because it is without replacement sampling, for the unit I to be included in the sample, there are only two chances. Either right in the very first attempt or in the second attempt. That's it. In the very first attempt, all the p vector is used, p1, p2, pn, and the chance of the unit I to be included is pi. That's why pi, that refers to the first attempt. And then if it is something else in the first attempt, it has to be some j different from I, that is what is pj. And once you select the jth item, because it is without replacement sampling, jth item is deleted. The moment you take it out, now you revise the probability computation for all other units, and there this divisor 1 minus pj comes. 1 minus pj is nothing but sum over all pi is different from j, because j is already selected. So pi over 1 minus pj, that is the conditional probability of selecting unit I, given that j has been selected beforehand. And this quantity summed over all j different from I, that refers to, you must remember that in this summation sign, whenever we are writing j not equal to I, we have to be very clear about it. Here j is the running symbol and I is fixed, because we are referring to the computation of pi I. Okay, and that simplifies to this thing. Easy simplification. What about the joint probability?
The joint inclusion probability of units I and j, pi ij, is pi pj divided by 1 minus pi plus pj pi divided by 1 minus pj, which is pi pj whole multiplied by 1 divided by 1 minus pi plus 1 divided by 1 minus pj. I hope I'm correct, but only so much for n equals 2. In general cases are not difficult, but I would say pretty much involved. I have no clue whatsoever about the method of estimation of the population mean, capital Y bar, or the population variance, capital S squared. No clue at all.
Yeah, so let's see again. Pi ij, as you rightly said, pi ij joint inclusion probability of the units I and j, and the sample size is 2. There are only two possibilities, I followed by j or j followed by I. If it is I followed by j, first one is pi and j is pj over 1 minus pi, and if it is j followed by I, pj times pi over 1 minus pj, then after that it's pretty simple simplification. You are very right. These are also for sample size 2, 3, it is possible to work out inclusion probabilities for first order or second order under PPS without replacement sampling, under unequal probability without replacement sampling, using the basic P vector, P1, P2, P capital N. All the time we are using P and inducting without replacement sampling. So let's see how the estimation procedure is coming. Okay. Whatever you have said about the methods of sampling is good enough to give a head start. Historically, these PIs relate to some kind of size measures derived in a way from some kind of auxiliary information available beforehand. As we talked about that the household size acts as an auxiliary information. If it is a crop survey, crop yield survey, then the sizes of the plots, agricultural plots, they provide size measures, auxiliary information. So that is how the PIs are related to some kind of size measures derived in a way from some kind of auxiliary information. All positive valued, these are denoted by x1, x2, xn. The size measure characteristic being itself denoted by capital X, and its values for the capital N units in the population are denoted by x1, x2, xn. They are positive valued real numbers, and they are converted into norm size measures pi xi over x summation xi, and that is what we are referring to as the p vector. So p vector comes out of the size measures which are already available to us, and those size measures, they are all positive valued real numbers. In reality, those could be household size, plot size, etc. The number of branches in a tree, if we are talking about yield of something in different trees, number of branches could be an auxiliary size measure, etc. And then these PIs are computed, and they behave as the PIs in the methods that we are discussing. So to conclude, in this module we have talked about unequal probability sampling, the fact that under simple random sampling, be it with or without replacement, all the population units are treated with equal importance, or they are given equal chance of selection. That bothers in reality, because there are evidences where the units should not be treated as having equal importance. For example, household survey, the household sizes are different. The yield crop cutting survey, the crop production survey, the sizes of the plots are different, and there is no reason why all the plots should be treated with same chance of selection. So that shows why in reality we need to have some kind of unequal probability sampling. We talked about unequal probability sampling using a basic P vector, P1, P2, P capital N. How it arises in practice. To start with, we have the size measures or the auxiliary size measures denoted by x, whose values are x1, x2, xn. These are some positive real numbers, and then these are normed. The norm size measures are the PIs, PI equal to xi over the total xi. That is how the PIs come belonging to 0 to 1, total equal to 1. These P1, P2, Pn, they act as the P vector in the definition of unequal probability sampling. It could be with replacement, it could be without replacement. We tried our hand in working out the inclusion probability at first order and second order under unequal probability sampling for both with and without replacement. Whereas for with replacement, the formulae are quite general, as you could see. The formulae for without replacement seem to be quite complicated. So we are able to see the result for small n equal to 2 explicitly, and looks like general case is very difficult, even though we can try our hand with n equal to 3 or 4, etc. But the things are complicated. But the point is that we need to go forward to find out what are the sampling methods and what are the estimation methods for estimation of the population mean and the population variance. Because these things intrinsically depend on the computation of first and second order inclusion probabilities. At least in some sense, we need to put our hands in the computation of these quantities, even for simple-minded designs. So the purpose of the exercises and MCQs in this particular module, module 4, are to train ourselves to make sure that we are comfortable in the computation of the first and second order inclusion probabilities. Then we will get back to more on the estimation and inference methods in module number 5. Okay, with this we stop. Let us now try our hand on the exercises. Okay, as I say, involving the questions, we will talk about computation of first and second order inclusion probabilities, but in a bit tricky sampling situation.
A without replacement sample of size small n more than 1 is to be drawn from a population of capital N more than 2 units. For the first unit to be selected in the sample, selection probabilities P and 1 minus P are attached to the first 2 population units with P in 0, 1. For the remaining n minus 1 units to be selected in the sample, simple random sampling without replacement, capital N minus 1, small n minus 1 sampling is adopted. Work out all first order and second order inclusion probabilities. Verify the relations summation pi I equals n, summation j unequal to I, pi ij equals n minus 1 pi I for each I, and double summation over I and j, I naught equals j, pi ij equals n times n minus 1.
Oh, this is one of my very favorite questions. When you are talking about a sample of size small n without replacement, all of them are distinct. So for the first one that you are trying to get, you only lay two probabilities, probability p for the unit number 1, probability 1 minus p for the unit number 2. So the first unit to be selected, it corresponds only to the two units in the population, either the first one with probability p or the second one with probability 1 minus p. Having done that, you still need n minus 1 out of capital N minus 1. That you get by adopting without replacement sampling. This is the sampling scheme. Very easy to conceive and very easy to adopt. Under that scheme, you are supposed to find out first order inclusion probabilities and second order inclusion probabilities for all units. Note that when you are talking about the unit number 1 or unit number 2, unit number 1 can come in the beginning or it can come also among the latter. Unit number 2 can come in the beginning or it can come among the latter, and all others can come only starting from second attempt onwards by the description of the sampling scheme. It's a good problem. And then these are indeed again very interesting relations. They apply to more general sampling schemes, but here once you compute all these pi I and pi ij's, you are supposed to verify these relations. So there are three relations given here. The first one refers to pi I total, the third one refers to all pi ij total, and the second one refers to for every fixed I, the sum total of all pi ij over all j. This is the running symbol is j. Good question. What is the next one?
With reference to without replacement sampling selection method in question 1, suppose n equals 3 and the sample selected is s equals 1, 5, and 8, while capital N is 10. Work out pi I and pi ij values for the units in the sample S. Examine the validity of the following results. Pi 1 times pi 5 more than or equals pi 1, 5. Pi 1 times pi 8 more than or equals pi 1, 8. Pi 5 times pi 8 more than equals pi 5, 8. Further, check if the above results are valid irrespective of the choice of the value of p lies in 0, 1.
Okay, so we are referring to the question 1 and the without replacement sample selection method, and we are referring to small n equal to 3, and we are referring to capital N equal to 10. So there are 10 units in the population. For the first unit in my sample, I use the sample population unit 1 is selected with probability p, population unit 2 is selected with probability 1 minus p, and after that the remaining two units are selected by without replacement sampling from the remaining n minus 1, that means 9 units. The particular sample selected is 1, 5, 8. That means in the first attempt you got 1 out of 1 and 2, and after that you got 5 and 8. Now you are supposed to work out pi I values for the units in the sample. So pi 1, pi 5, pi 8, pi 1, 5, pi 1, 8, pi 5, 8. Once you do all the computations, you are supposed to verify whether these relations are true or not, just validating the results. And then you have to say if at all these are true, you have made a choice of p, or irrespective of the value of p, these can be validated. Okay? Good question. The next one.
With reference to without replacement sample selection in question 1, suppose small n is 3 and the sample selected is s equals 2, 1, 8, while n equals 10. Work out pi I and pi ij
Similar question.
values.
Okay. The interesting point is this time the units in the sample, the first one is 2 out of 1 and 2, but still even though 1 is not selected in the first attempt, there is a possibility of 1 coming up later because it is under without replacement. That's how 1 comes in in the second attempt. So you got 2, 1, 8. You are supposed to work out pi 1, pi 2, pi 8, etc. So the questions A, B, C, they relate to your computations and then verifying these inequalities. Very good. And the same question, whether it depends on the choice of P in the description of the taking up the first unit from the population, whether it depends on the choice of P. Very good. What are the MCQs?
With reference to question 1 above, all first order inclusion probabilities are equal when p is half. Is it always true? True for some values of n more than 2, or never true?
Very good question. It says, so for the first unit to be taken up in your sample, you take p equal to half. That means you give 50-50 chance to the population unit 1 or the population unit 2. Give a 50-50 chance to them. And after you have selected one of these two, then you go for simple random sampling for the remaining ones. Having done that, is it true that in the process all first order inclusion probabilities will be the same? Is that always true? Or it will be true for some values of capital N, or it is never true? Interesting problem. What is the next one?
With reference to question 2 above, it is claimed that pi 1 is more than pi 5, which is equal to pi 8. And 2, pi 1 5 equals pi 1 8 more than pi 5 8. Are both true?
Okay.
Are both false? One is true and 2 is false, or one is false and 2 and 2
okay.
is
So once
true?
you work out these things, you can see, and then you have to think more about interpretation of these results. Okay. What is the next one?
With reference to question 3 above, it is claimed that pi 1 is more than pi 2 if and only if p is more than half, and pi 1 2 is more than pi 1 8 and pi 2 8, whatever the value of p. Only one is true, both are true, or both are true if and only if p is half.
Interesting questions. Yeah? You have to think about it. There are many theoretical results available in a very general setup. We will have a test of some of these results when we go ahead with the next module.